Hello and welcome back to educator.com and welcome back to biochemistry. So in the last lesson we finished off our discussion of the glycolytic pathway. I'm going to continue and talk a little bit more about glycolysis, but what I'm going to talk about in this lesson is the feeder pathways to glycolysis. Basically all of the carbohydrates in the body, how do they enter the glycolytic pathway? And then after that, I'm going to talk a little bit about the fates of pyruvate. So you remember pyruvate was the final molecule, the two molecules of pyruvate that glucose was converted into. I'm going to talk a little bit about what it is that happens to them, lactic acid fermentation and ethanol fermentation. So let's go ahead and get started. Okay. So as you can see, this first page here, there is a lot going on. So what I have here are the feeder pathways, the pathways that other carbohydrates in the body take in order to get to glycolysis. So for example, when you eat regular table sugar, sucrose, what does the body do to that? How does it take that sucrose and how does it metabolize it? Does it go through the glycolytic pathway? Does it take another pathway? What is it that happens? Your starch that you eat, glycogen, what happens to these things? And that's what's going on here. So I'm just going to run through each individual pathway. We're not going to really get into a lot of detail, but I do want you to see where each thing goes, where it comes from. I think it's really, really important. So what I have here are, in boxes, the major sugars that we're concerned with. So I have the starch and the glycogen. Fructose, sucrose, here is glucose, of course, the central position. Well, it's not central here, but it's, glycolysis, glucose. Trehalose, lactose, galactose, and mannose. These are the primary carbohydrates for the body, and we want to see what happens to them. Now, in red, you're going to see the enzymes that actually catalyze these particular transformations. And of course, this in blue, 1, 2, 3, I'll talk about them in a little bit. It's going to talk about the dietary pathway for a particular carbohydrate, or the tissue pathway for a particular carbohydrate. And of course, there is the liver pathway. So that's going to be 1, 2, 3, and I'll get to those when I actually talk about those individually. So I guess the best place to start is right in the middle. So I'm going to start with starch, and I'm going to start with glycogen. So starch. So look over here, we have the starch. So let's say you happen to eat some starchy food. Well, the dietary pathway, what happens is the enzyme alpha amylase starts to break down the starches starts to break down the starches. You have alpha amylase in your saliva that actually does the first phase of breakdown. And then, of course, once it goes into your stomach, that enzyme is actually neutralized, and another alpha amylase takes over in your intestine. So eventually what happens is it's all converted into glucose. And once it's glucose, then it can start the glycolytic pathway. Hexokinase plus ATP goes to glucose 6-phosphate, and of course it'll just continue on and get to the end of the glycolytic pathway. So starch passes through glucose and into the regular glycolytic pathway. Now, as far as glycogen is concerned, you remember we talked about the carbohydrate glycogen. Glycogen, your body stores glucose units as this polymer called glycogen. And if for any reason, if your blood sugar drops too low, the body mobilizes this glycogen. Remember, it's highly, highly branched. It goes and it breaks off all those glucose units and it sends them into the glycolytic pathway. So what happens as far as the cellular tissue pathway for glucose to enter the glycolytic pathway, a glycogen, an inorganic phosphate comes in, and this enzyme called phosphorylase actually breaks off individual monomers from the ends of the glycogen molecule. It's converted to glucose 1-phosphate. Well, glucose 1-phosphate is then converted to glucose 6-phosphate by the enzyme phosphoglucomutase, and now that it's glucose 6-phosphate, it can just continue on into the glycolytic cycle. So you see how that happens: dietary and then cellular tissue pathway. Okay, so let's talk about galactose. Let's talk about lactose. So lactose is that disaccharide, which is glucose and galactose. So what happens is lactase ends up breaking up that disaccharide, and the molecule of glucose goes on normally into the glycolytic pathway. the galactose monomer, it goes through a couple of conversions. It's turned into uridine diphosphate galactose, uridine diphosphate glucose, and then that's converted to glucose 1-phosphate, and then the glucose 1-phosphate, as we see here in the center, is converted to glucose 6-phosphate, and then it can go on and continue in the glycolytic pathway. Okay, so now let me see. So we've taken care of lactose, we have the glucose, we have starch and glycogen. In the case of mannose, mannose is converted into mannose 6-phosphate, and then it's converted to fructose 6-phosphate. So it's a little further down the glycolytic pathway, but that's how it enters glycolysis, which is right here, this central pathway right here. Trehalose. Trehalose, the enzyme trehalase, breaks it up into glucose monomers, and glucose enters the glycolytic pathway as usual. The sucrose, the table sugar that you eat, it is a disaccharide of glucose and fructose. Well, the sucrase breaks it up. The glucose enters the cycle normally. Fructose, it has two possible fates. One possible fate is when fructose, by the action of the hexokinase plus adenosine triphosphate, is converted to fructose 6-phosphate. It can enter the glycolytic pathway that way at fructose 6-phosphate. Or in the liver, what the liver does is this fructokinase converts fructose to fructose 1-phosphate, and then fructose 1-phosphate aldolase takes the fructose and breaks it up into two molecules, glyceraldehyde and dihydroxyacetone phosphate. Now, the glyceraldehyde is converted by triose kinase to glyceraldehyde 3-phosphate, and now it can enter the second phase of glycolysis, so it comes in down halfway through the glycolytic pathway, and the dihydroxyacetone phosphate, as we know, is converted by the triose phosphate kinase, again into glyceraldehyde 3-phosphate, and it enters the glycolytic pathway that way. So that's it. I'm not sure about the extent to which your particular teacher is necessarily going to have you memorize this entire thing. Perhaps he or she will want you to know at the very least, maybe the dietary pathway for starch and the cellular tissue pathway for glycogen, but I did want you to see it. So all of the carbohydrates that you eat, somehow or other, they all end up in the glycolytic pathway. That's it. That's what's going on here. Okay, great. So now let's go ahead and talk about the fates of the pyruvate that's formed during glycolysis. So we take this glucose molecule, we break it up, we subject it to 10 steps, and we end up with these two molecules of pyruvate. Well, what happens to pyruvate? Well, we know what happens to pyruvate aerobically. Well, I'm going to tell you right now. So let me see. Let me go do this in blue, I think. So let's talk about so under aerobic conditions, so when there is plenty of oxygen to go around, so under aerobic conditions, the pyruvate that's formed, pyruvate continues on and is oxidized to a molecule called acetyl coenzyme A. And it enters the citric acid cycle, the Krebs cycle, and enters the citric acid cycle. Eventually becoming CO2 and H2O once it enters the electron transport chain. Now, the NADH from glycolysis, remember, we actually form two molecules of NADH, those 4 electrons. It passes its electrons to the electron transport chain, becoming NAD+ again. This is important. Under aerobic conditions, when there's enough oxygen available in the body, when the cells have enough oxygen to work with, the NADH that's formed in glycolysis can actually pass its electrons to that oxygen. because that's what the electron transport chain is. It takes those high energy electrons from these coenzymes and it passes them along a chain, and ultimately it's oxygen that ends up taking those electrons. It ends up being reduced. That's what oxygen does. Oxygen oxidizes things. It itself gets reduced. So when there's plenty of oxygen, the NADH can actually turn back into NAD+ when it gives up its hydride, when it gives up its electrons. That's very important because we need to regenerate the NAD+ so that glycolysis can continue with step 5. We need that NAD+ to make, step 6. We need that NAD+ because we need to oxidize that glyceraldehyde 3-phosphate. If we run out of NAD, if NADH cannot give up its electrons, glycolysis comes to a halt because there's not going to be enough NAD+ to keep glycolysis going. That's what's going on. So under aerobic conditions, when there's plenty of oxygen, everything is fine. NADH goes to NAD+, and glycolysis can continue. Now, what happens under anaerobic conditions? Well, under anaerobic conditions or hypoxic conditions, low oxygen or no oxygen, what's the NADH going to do? It has to give up its electrons somehow because it has to turn back into NAD+ so that it can go back and actually continue doing its work on glycolysis. Well, the body has figured out a way to do that. So now, the anaerobic fates. The anaerobic fates of pyruvate. All right, so under hypoxic conditions, well, I'm going to say hypoxic anaerobic, so either low oxygen or no oxygen. Anaerobic conditions. NADH cannot pass its electrons to oxygen because there is no oxygen. Cannot pass its electrons to O2 to become NAD+ again. And a depletion of NAD+ stops glycolysis. We don't want that to happen. When glycolysis stops, very, very bad things happen. Now, NAD+ must be regenerated somehow. Must be regenerated somehow. Okay, now cells do this. Cells do this by transferring their electrons, the NADH, to pyruvate, directly to pyruvate. To pyruvate to form lactate and or ethanol. Or ethanol. In other words, we're reducing pyruvate. We're passing electrons to pyruvate in the form of hydrides, in the form of hydrogen. So, transferring electrons to pyruvate. All right, we are reducing pyruvate. Okay, the first of these methods is lactic acid fermentation. So let me go ahead and actually start this on the next page. I think I'm just going to do this in red for a change of pace. So the first fate of pyruvate is lactic acid fermentation. This is what your body does. Lactic acid fermentation. When you are heavily exercising, your body starts to crave oxygen. You start to run out of oxygen. When there's not enough oxygen for the body for regular aerobic cellular respiration to continue, the cell has to be able to regenerate that NAD+ to keep glycolysis going. In order to do that, it takes the pyruvate that's formed in glycolysis and it converts it to lactate. That's the sore that you feel. when your muscles start to give up, when your muscles start to fail, that soreness that you feel, that's the lactic acid, the lactate building up in your muscles. Okay, so lactic acid fermentation. So here is the chemistry. So this is CH3. So we have our pyruvate molecule. And it is going to go like this. NADH plus H plus in and NAD plus out. NADH gives its electrons to pyruvate and converts it to lactate. C, C, C. This stays H3. This becomes OH and H. O minus. This is pyruvate. This is lactate. This is actually L-lactate. Lactate. So I'm going to draw it this way. I'm going to put the OH over here. It's L-lactate. Okay? We've taken this carbonyl, this double bond, and we've added 2 hydrogens across the double bond. Okay? The carbonyl is here. We've added a hydrogen to the oxygen, a hydrogen to the carbon. We've reduced the pyruvate. In the process of reducing it, we've actually recovered NAD+. Now glycolysis can continue. Now the body can do something else with the lactate. That's what's going on. Now the delta G for this reaction, go ahead and put that there. It's pretty high actually. Delta G is negative 25.1 kilojoules per mole, or I should say low, depending on, the number is high, but it's negative. So this is a highly exergonic reaction. Okay, that's it. So let me draw the, so glucose is converted into pyruvate via glycolysis. Now pyruvate is converted into, let me make this arrow a little bit longer, is converted into lactate, and we have NAD plus in, NADH, that's the cycle. Glucose, step 6, NAD plus in, NADH out, goes to pyruvate. This is glycolysis, what we just did. Under anaerobic conditions, NADH gives its electrons, gives its hydrogens to pyruvate, reducing it to lactate, and in the process recovering NAD+, so that the cycle, so that the glycolytic cycle can continue. Otherwise, the glycolytic cycle will stop and bad things happen. Okay. Now, probably should have done that up. That's okay. All right, some cells, like erythrocytes. Erythrocytes, they don't have mitochondria. They have no mitochondria. So they cannot metabolize under aerobic conditions, because that's where oxidative phosphorylation takes place in the mitochondria. They have no mitochondria. So they do this. They do this lactic acid fermentation even under aerobic conditions. That's how they regenerate the NAD+. They do this even under aerobic conditions all the time, even under aerobic conditions. Okay, so that's lactic acid fermentation. Now we'll talk about the other fate of pyruvate, ethanol fermentation. I think I'll go back to black for this one, just for a change of pace. So, ethanol fermentation. Okay, yeast. Ferments glucose to ethanol. So the pyruvate, that glycolysis, so yeast takes glucose, goes through glycolysis, converts it to pyruvate, but now, instead of lactic acid, instead of lactate, it actually produces ethanol. That's how we get our ethanol. That's how we get our drinking alcohol. Okay, So what we have here is C, C, and C. So we have that, and we have this. So this is a two-step process, actually. I'll go ahead and do this. CO2 is released, and the enzyme is pyruvate decarboxylase, and it also requires a coenzyme called TPP. TPP is thiamine pyrophosphate. It is the coenzyme that is derived from vitamin B1, which is thiamine. And it also requires magnesium ion. So this is the enzyme. It requires this, and it requires that. So let me go ahead and write what TPP is. And I will talk about it in a minute. I will do this mechanism. It's very, very important. TPP, profoundly important coenzyme, as you know. Vitamin deficiency, bad things start to happen. So TPP is thiamine pyrophosphate. And don't worry, we'll be drawing all of this out in just a minute. So the first thing that it does is it converts it into CH3. It converts it into acetaldehyde. So it takes the pyruvate and it actually knocks off this carboxyl group. It goes away as CO2. This COO minus this carboxyl group goes away as CO2, leaving just the acetaldehyde. And then the second step, we have, this is where the NADH comes in. It gives its electrons over, it regenerates NAD+, and it produces our famous ethanol. There's H there, there's H there, and there's OH here. Here we go. And this is alcohol dehydrogenase. Dehydrogenase. Okay. There you go. All right. Now let's see, what else do we want to say? So the ethanol fermentation, pyruvate, first step is catalyzed by pyruvate decarboxylase to form acetaldehyde, and acetaldehyde is converted into ethanol. So let me go ahead and write those out. So this is ethanol, this is acetaldehyde, and this is pyruvate. Okay. There we go. Now, thiamine pyrophosphate. Okay. So let's go ahead and talk about the thiamine pyrophosphate, and let's talk about this first reaction, the pyruvate decarboxylase reaction. Okay. So let me do this in blue. Wonder if I can draw the structure. Well, that's okay. So TPP, as we said, it is a coenzyme that is derived from thiamine, which is vitamin B1. So you ingest the thiamine, the vitamin B1, and the body converts it into its active form, which is a thiamine pyrophosphate. It adds a pyrophosphate onto this structure that I'm going to draw in a second, and then it goes ahead and does what it does with this enzyme, pyruvate decarboxylase. Okay, so let's go ahead and work on some structures here. So let me go ahead and do this in blue. I think I'll do this structure in black, actually. So I've got a little six-membered ring here, got a nitrogen up here, got a nitrogen up here. This is aromatic. I have NH2. I've got CH3. I've got a CH2 group here. I've got a, let's see, I've got a, here is where we get really, really interesting. So there, this is carbon, this is sulfur, and I'll go ahead and put that there. Go ahead and do that. Don't worry, I don't think you're going to have to memorize the structure for thiamine pyrophosphate. It's the mechanism that's important. So this is going to be a plus charge on there because we have 4 things attached. We have, of course, a hydrogen there, a sulfur, and let me see, what else do we have? Aha, we have CH2, we have CH2. Now we have our pyrophosphate. We have O, P, O, P, O. There we go. Let me go ahead and make sure all the oxygens and charges are there. So this is TPP. This is thiamine pyrophosphate. What's important is this thing right here, this ring. Okay, this is called a thiazolium ring. This is this thiazolium ring. All of the chemistry takes place at that carbon, okay? And you're accustomed to this already, you know, just like when we did NAD+. All of the chemistry takes place at one place. The rest of the molecule is just used for, basically the enzyme uses it to hold it, to bind it, to make sure everything, it's a handle. All of the chemistry usually takes place in one location over and over again. It's not multiple locations. Okay, now the H, this H right here, the H on the, oh, let me number these, by the way. This is number 1, number 2, number 3, number 4, and number 5 on this thiazolium ring. So the H on the number 2 carbon, of the ring, well, there are 2 rings of the thiazolium ring, of the thiazolium ring is acidic. Acidic. And when it's lost, when it's deprotonated, and when lost, it creates a nucleophilic carbanion. Creates a nucleophile, a nucleophilic carbanion. So a carbon that's actually carrying a little bit of a negative charge. As you'll see in a minute, that negative charge is stabilized, but it's carrying a negative charge, so it's highly nucleophilic. Okay, carbanion that adds to carbonyls. Okay, that attacks the carbonyl carbon. That adds to carbonyls. Okay, now let's go ahead and see if we can make sense of what's going on. So let's go ahead and do this mechanism. I'm going to try to do the mechanism on 1 page. Hopefully I'll be able to do it. If not, well, that's okay. We'll go to 2 pages. Let me see if I should go here first and then here. No, that's okay. I want to have it all on 1 page. So let me go ahead and do this in black, and then I'll probably do the electron moving in red. All right, so we're going to concentrate just on that ring. So we've got, let me go ahead and draw this first. I've got N, I've got C, S here, I've got R1, R2, and I've got a double bond there. This is a positive charge. I have this H, and I have CH3. Okay, so everything starts when, so we said this proton here on the number 2 carbon of the thiazolium ring is acidic. When it's lost, so I'll do it this way. When it's lost, what you end up with is this carbanion. So we've got R1, I've got N. I'm going to draw this a little bit better. N, S here. So there's now an electron there, and it's a negatively charged. So this is plus, this is CH3, this is R2. Have I forgotten anything else? Nope, I think everything is good. And now we have our pyruvate. So let me go ahead and draw my pyruvate molecule. I'll go ahead and draw the pyruvate in blue. This is C, C, and C. I've got O minus. There's that carbonyl, right? Pyruvate. And this is CH3. So what it's going to do is actually going to attack the carbonyl, like we said. So I'll do this in blue. So it attacks the carbonyl, and this goes and actually grabs a hydrogen ion, and it becomes the following. So we go to Let me go just here because I'm going to need some room. Let me see, I've got, well, you know what? It's okay. Let me go back to black. So I've got R1, boom, this is N, this is C, S, there, there, there. Now I've got myself a C. I've got a C, O minus. Here I have, oops, I'm sorry. I decided to do this in blue. I think it's probably best if I do it in blue. So let me go ahead and just make sure that everything else is on here. So I've got a double bond, a positive charge. Let me go ahead and write my R2 here, my CH3 here. Now let me go to blue and let me do, and I'm also going to move my arrow. I'm going to put my arrow over here so I've got some room. So now I'm in blue, and now I've got C, I've got C, I've got C. This is H3. This is now OH. And this is O and O minus. Okay, so far so good. So this carbanion, right, nucleophile, it attacks the carbonyl. The carbonyl, this goes ahead and grabs an H from the surrounding medium to become an alcohol group right here. Now what happens is the following. This, oops, let me do this electron movement in red. That bounces down there. This bond breaks. This bond breaks. This goes off as CO2. This bond breaks and forms a double bond here, and it forces these electrons onto the nitrogen, which is carrying a positive charge, so it actually quenches the positive charge on that. So what we end up with is the following. Let me go back to black. So CO2 is gone. And now we have, let me see, boom, boom, I'll do N, I'll do S, that, nope, that's not there anymore because these electrons moved. Okay, this is R, and now we have this double bond, which I'll do in blue in just a minute. This is there. Let me see, this is R2, this is CH3. Now I'll go back to blue. Now we have a double bond, we have a C, and we have an OH, right? And we have a CH3, so that's what's there. Now, this actually undergoes a little bit of resonance. So, these electrons were pushed onto nitrogen. Now, what happens is these electrons are going to go like that, and they're going to go back up to the carbon here. So we have this resonance structure. We draw this in black. So we've got, let me see, nitrogen, sulfur, that. So now we have a single bond, we have a C, we have these nope, I said I'm just going to do that in blue. I keep forgetting I don't want to do that in black. So this is R2, this is R1, this is CH3. Now let me go to blue. So now I have this carbon with 2 electrons on it, and that, it has a hydroxy group, it has a CH3 group, and this right here is your resonance stabilization right here. So there's a double arrow, single double arrow, resonance. So once we form this, these electrons can bounce back up here and actually stabilize. So this negative charge on the carbon is actually stabilized because it can redistribute itself and actually come, and the nitrogen is actually sharing that negative charge. That's why this works. Okay, now what we have is the following. Once we have this, let me see, where are we? Let me make sure. Hydroxyethyl TP. I wonder if I should go ahead and do it that way. Okay, that's fine. I'll go ahead and go here. I know there's a lot going on. Don't worry. We'll make sense of everything here. So this is N, and this is S. We have that, okay. And then we have, let's see, we have our R1, we have R2, we have that, we have our CH3, okay. And now I've got the C, and I've got the O, and I'll write the OH that way. I've got the CH3, okay. And let's see, I'm going to draw a little bit of an H plus here. So because this carbanion, basically what I'm going to do, it takes a hydrogen ion from the medium to become that, okay? So forms this, there's resonance stabilization here, a hydrogen ion attaches to here, so now you have this thing attached, okay? And now here's what happens. These electrons move here. These electrons go and grab a hydrogen ion, okay? And what you're left with is, so here's where I definitely should have gone to the other page. So now, what happens is, what ends up leaving is our acetaldehyde. So I'll do this in blue. So this. So once this grabs this H, this bond over here to the thiazolium ring actually breaks. And what you end up with is the following molecule. You end up with C, C, O, H, CH3. That's this thing. This C, O, O, that's this. This H is this H, and this CH3 is that CH3. So this is our acetaldehyde. That's what the enzyme ends up actually releasing. And then once this happens, you're back to the form that you were before. Okay? So this goes and grabs this H plus. That becomes this H. This comes here. This H is this H. This O is this O. This carbon is this carbon. And this CH3 is this CH3. Okay? So this H that this bond grabs, it recovers the thiazolium that is protonated, and then it can begin the cycle again. So let's run through this one more time. We have the thiazolium ring on the TPP, we lose a proton, and we form this nucleophilic carbanion. This nucleophilic carbanion attacks the pyruvate, the alpha keto on the pyruvate, okay? And when it does that, it's now attached to it covalently. Now, of course, it's primed because now there's a place for electrons to actually go. This is called an electron sink. This positive charge on the nitrogen it pulls electrons toward it. And when it does that, it makes it very, very easy for this negative charge on the oxygen to actually form a second double bond with carbon to form CO2. CO2 is a very stable molecule. This happens a lot in biochemistry. Decarboxylation, forming CO2, happens very, very easily. So it forms the CO2. This CO2, this bond breaks, so CO2 is lost in this reaction. And what you end up with is this structure right here. Well, these electrons push back up. They form the carbanion again. So this is a resonance structure. So this negative charge is actually shared between the carbon and the nitrogen. If you want, you can think of this actually grabbing another hydrogen from here to become this thing. Okay, a hydrogen comes in and becomes this. And now these electrons go over here to form a double bond. These electrons are pushed and they grab a hydrogen ion to recover the thiazolium, which is protonated, and of course the acetaldehyde goes away. So this is the this is the pyruvate decarboxylase reaction. This is the first part of the ethanol fermentation process. We won't go ahead and talk about the second part. That's just a dehydrogenase reaction. We may talk about it later, we may not, but I definitely wanted you to see this. So this is our first introduction to a major coenzyme, the thiamine pyrophosphate. Okay, We're going to go ahead and close off our discussion of this phase of glycolysis for today. Thank you so much for joining us at educator.com. We'll see you next time. Bye-bye.